probabilities. So we're going to come up with the chances that this experiment takes 2 rolls, or that it takes 3 rolls, or that it takes 4 rolls, or that it takes 5. Okay. Now, there's a couple ways we can do this, and I'd like to focus primarily on the methods we started learning about in the last project. We can also do this with something called the fundamental counting principle. If you had me in Math 105, we've talked about it before. If you haven't, we'll talk about it soon. So I'm gonna kind of allude to it here and then pull back from it and use just the stuff from our last project. Let's look at the 2-roll option for a 4-sided die. So if you roll a 4-sided die twice, you have to realize that each of the rolls has 4 possibilities. So the rolls could go 1 and 1, 1 and 2, 1 and 3, 1 and 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, or 4, 1, 4, 2, 4, 3, 4, 4. Now, those of you that have had me in Math 105 or have seen the fundamental counting principle before would have known automatically that there were 16 total outcomes, because there are 4 ways for the first thing to happen and then 4 for the second. Now, some of you sitting there going, I ain't never heard of that thing before, and that's okay. We don't have to look at it that way. But if you have seen it before, you know these are the 16 possibilities, which means you also can look at all 16 possibilities and realize that there are 4 of them that have a repeat. So the answer, the probability for this should be 25%, 4 out of 16. Now, how do we get that without the fundamental counting principle? Well, let's break it down using stuff from the last project. In order for it to take 2 rolls, that means we have to roll a die and then have the second die match the first one. So I say we break this down using fractions for probabilities. Let's roll the first die. Now, ask yourself this. What are the limitations on that first die? Am I being specific about it? Am I saying I have to roll a 1 on the first die? No. I'm just saying I want to get a repeat. So really, there is no limitation on this first die. Now, I know that first die is out of 4 possible sides. And if any of the 4 possible sides can work, then really there's a 4 in 4 chance, or 100% of the time, whatever I roll is going to work. Now, that might seem a little silly. Why would you even bother writing that down? Well, I'm trying to tie it back to that last project we just did. The interesting thing happens with the next die. Now, the next die still has 4 options. Remember, when you pick the die back up and throw it again, there's always going to be 4 options. That's kind of what makes dice. But here's the catch. I want this die to match this one, which means whatever fell on this one has to match it, which means there's only 1 possibility left for that second die. Which means you've got a 4 times 1, which is 4. This is going to sound familiar. 4 out of 16 shot that it's going to take 2 rolls to get a repeat. 25% of the time. Doesn't matter what happens on the first. What matters is what happens on the second. Okay, good so far? Okay. Now it gets a little more fun with 3 rolls. 3 rolls, well, first of all, we could do it with the fundamental counting principle, but we're not, and you'll see why in a second. Let's do it with Project 2 Math, which means we first have to roll a die, which is going to have 4 options. Then we're going to have to roll a die again, which has 4 options, and then we're going to have to roll a die again, which also has 4 options. Every time I roll the die, I've got 4 more options. Just like in the 2 case, it doesn't matter what happens first. But here's where it gets fun, I think. There are 4 options for the second die. But we want to make sure that it takes us 3 rolls. So that tells us whatever happens here has to be different than what happened here. So anything could have happened here. That's why this is a 4. But now here, you've only got 3 options, because this can't match this. By going 4 over 4 times 3 over 4, you're guaranteeing the first 2 rolls are different. But we also want to be done on the 3rd roll. What that tells us is whatever happens here has to be the same as either this one or this one. So this one is different than this one, but there still are two outcomes here and here. This one has to be one of those two outcomes. So the chance of it taking 3 rolls to get a repeat is going to be 4 times 3 or 12 times 2, which is what? 24 over 4 times 4 times 4, which is 64. And that right there, hopefully you appreciate why I didn't want you writing out all the possibilities, because you'd have to write 64 of them out. But this is nice because we actually get to the fraction we need without having to write them out. Let's keep going and do the 4 case and the 5 case. Might run out of board a little bit. I may have to kick this in a little bit because we're running out of space on our right side of the board here. Okay, with 4, we know we're going to have to roll 4 fractions, or four dice, which means we're going to have 4 fractions. This one here, this is going to sound kind of boring, can be anything. It can be any of the 4. This one here can't match that one. So that means it's only got 3 options left. This one here can't match either of these 2 because we have to roll it 4 times. This is only the 3rd roll here. So this one can't be this one. Let's put all the possibles out here. It can't be this one, and it can't be this one. So it can only be one of these 2 remaining. That looks like this so far. Now here's the interesting one. We want to be done here, which means we now have to either match this one, or that one, or that one, which means we've got 3 shots to be done by there. So we end up with 4 times 3, which is 12, times 2, which is 24, times 3, which is 72, out of, check my math on this one, 256. Whoa! So we're getting there, friends. We're getting there. Now, the last one down here, depending on how fancy you want to get, we could actually do this straightforward. As a matter of fact, let's take a look at this the way we would have done it in the last project, before we had even learned about all these multiplications of probabilities. Okay, I cleaned up the distribution a little bit for us to get rid of all the work that we did. I put just the percentages that these things are equal to in here. So there's a 25% chance it's going to take 2. That was 4 out of 16. 37.5% chance it's going to take 3. That was 24 out of 64, and that's our mode. And then a 28.125% chance. That's the 72 out of 256 that we just got. Now, if you're clever, which I know you are, you could figure out what the 5th one was by just doing 100% minus the other 3. Now, I took the liberty of adding these up, and I think I got 90.625%. And if I take 90.625% away from that 100%, I get 9.375%. Now, for those of you that want to know how to do this using the fractions, in other words, how to get 9.375% multiplying 5 fractions together, watch the next video. Just a little miscommunication there. Sorry, Sean. If you want to see the multiplication, watch the rest of this video. Otherwise, skip to the next video, and we'll see how to take the average of this distribution. I knew some of you would come back and watch this, and some of you just fast forwarded, right? No, you're still here. What's the chance it takes 5 dice? Let's figure it out. So, we know we're going to have 5 dice to roll, so we're going to have 5 fractions to kind of populate. And we know that each of those is going to be out of 4 possibilities because it's a 4-sided die. And the pattern you've established with 2 and 3 and 4 still holds here. You're going to have all possibilities on the table for the first roll. Because the first roll doesn't tell you anything. It establishes, if you've played craps before, it establishes what's known as your point if you go down that road of craps. So I just rolled right now, it went on the floor, and I got a 4. So 4 is my point. But I could have gotten a 1, a 2, or a 3, so it really doesn't matter what I rolled here. What matters is, I don't want to match it here, which means I'm down to only 3 remaining possibilities here. And then here, I don't want to match either this or this, which means I'm down to 2 possibilities here. And then here, I don't want to match here, here, or here, which means I only have 1 possibility left for there. Now, right here, at this point, you have calculated the probability that if you roll 4 dice, they're all different. Assuming 4-sided dice. Then they're all different. They're all different. How about the 5th die? What can happen out there? Well, out there, anything can happen. Because whatever you roll right here is going to match something back here. So you're back to 4 out of 4 at the end as well. Isn't that wild? So mathematically, what it ends up being, we can actually be pretty slick with the math here. We can divide these off and call them 1s. We can call this a half. And I think that's all we can do simplification-wise. So the chance is going to be 3 out of, what did I just get here? 16 times 2 is 32. 3 in 32. And if you get that puppy dog, that's going to be your 9.375 that we just calculated by subtraction. So you can do it directly. You can do any probability in this way directly. Unfortunately, Math 243 is too short to really do this kind of, I call this super counting, where you can actually enumerate every aspect of a potential random variable. I'll do it here and there when it makes sense to do it here and there. But in all honesty, if you are in a major that requires this, you'll take entire courses devoted to this. This is just kind of scratching the surface. So thank you if you've kept watching this, and hopefully this has appeased your curiosity a little bit. Otherwise, let's move on to the next videos and figure out how to take the average. What is the average number of rolls it takes to get a repeat?